Hello Team GChem and welcome to today's lecture, where today we're going to be working through a slightly more challenging problem involving limiting reagents. And the problem statement we're given is that we have an unbalanced chemical reaction, and we're asked if we mix together 160 grams of potassium permanganate, that's that KMNO4 species, with 220 grams of hydrochloric acid, HCl, how much manganese 2 chloride, MnCl2, will you form, and how many grams of excess reagent will remain? So we're going to go through this problem in several steps. If you already feel that you're at a state where you're ready to work some of these practice problems, I would highly encourage you to pause the video at the beginning of each step and try and work it yourself. But as you might guess, step one is going to be that we need to actually balance this equation. I would say this reaction, especially because there's so many chlorines, is a great time to try and practice the algebra method, but I'm going to walk through this one using more of a guess and check approach. So when we're balancing equations, I like to start making a table of all the different elements that I have, and before I balance it, making a list for myself of what elements there are and how many I have of each element. So I'm going to start off with my chlorines, is the tricky one. I've got on my right hand side 1, 2, 3, 4, 5 chlorines. And as for my oxygens, I've got 4 and 1. So this is probably a pretty challenging balancing exercise. What I decided to do is first start with the oxygens, because I see that on the right hand side there's only one species that involves oxygen. And so if I start off with a coefficient of 4 in this spot, I can successfully fix up the number of oxygens that I have. However, that is also going to change the number of hydrogens that I have on the right hand side. And so my next step is going to be to put a coefficient of 8 in front of the HCl. That's going to fix up my hydrogens, but it's also going to change the number of chlorines that I have. And so the last thing that I want to do is I want to try and fix up the number of chlorines. And a trick that we can use is to recognize that the last species on the product side only contains chlorine. And so if we can fix that coefficient to fix our chlorines, this entire thing is going to be balanced. And on my right-hand side, I have from the potassium chloride and from our manganese 2 chloride, I already have 3 chlorines accounted for. So I would love for the last coefficient to somehow give me 5 chlorines. The only way that I can do that is if I temporarily put in this fractional coefficient of 5/2 in front of the chlorine. That's not allowed to be my final answer. Balanced equations should always be in terms of lowest whole number coefficients, but it can let me see that the only thing I need to do is count. Now I've got 8 and 8, and so this equation is balanced, and I'm just going to multiply all the coefficients by 2 in order to get my final answer. And so that's going to give me coefficients of 2, 16, 2, 2, 8, and 5. And you can go ahead and double check, and this equation is balanced. So now that our equation is balanced, the next thing that we need to do is we need to determine what is the limiting reagent. There are lots of different strategies for figuring out the limiting reagent, and I'm going to present to you one of them. But feel free to come talk to me in office hours. If this strategy doesn't connect with you intuitively, there are a couple different ways that you can approach limiting reagent problems correctly, and no one way is better than the other. But the strategy that I'm going to show you in this video is what we are going to calculate for each reactant that could be the limiting reagent. Here, that means potassium permanganate and hydrochloric acid. We're going to go through and calculate, if we were able to use up all of that reactant, how much manganese 2 chloride would it produce? And whichever of those two reactants forms the least amount of product is going to end up being our limiting reagent. So I'll show you what that mathematical process looks like, and then we'll talk through why this makes sense. To kind of organize my work, I did go ahead and put in the starting amounts that were given to us in the problem statement, and I also went through and for the 2 reactants and the 1 product that we're interested in, wrote down the corresponding molecular weights. So for potassium permanganate, we are going to try and figure out the number of grams of manganese 2 chloride that forms. That means we're going to need to do a grams to moles conversion, followed by a moles to moles conversion, last but not least, followed by a moles to grams conversion. And so dimensional analysis style, we are always going to be trying to cancel our old units diagonally to get to the new unit. So we're going to start off with our 160 grams of potassium permanganate. Go ahead and put that over 1. And then using our molecular weight, that is going to be what allows us to get into units of moles. Next up, I need to do a moles to moles conversion. So I need to figure out how many moles of potassium permanganate correspond to our moles of manganese 2 chloride. And this is where we had to start by balancing the equation, because the coefficients that we're going to get for this moles to moles conversion come directly from the balanced equation. And I see that I've got a 2 for the coefficient for manganese chloride and also a 2 for the coefficient for potassium permanganate. Last but not least, I need to do a moles to grams conversion, and so that is going to be using the molecular weight of manganese 2 chloride. And that is 125.84 grams. And when I put this all into my calculator, that is going to give me the number of grams of manganese 2 chloride, which after doing the math, you would get that this is 130 grams of manganese 2 chloride. Okay, so that's possible answer number 1. We now know that we've done this calculation that there's no way we're going to form more than 130 grams of manganese 2 chloride, because if we tried to form, say, 135 grams, the potassium permanganate is going to run out. What we don't know, however, is if the hydrochloric acid is going to be even more limiting. And so if HCl gives us fewer grams of manganese 2 chloride, that's going to indicate to us that maybe we actually like that HCl is going to be the limiting reagent. But let's go ahead and find out. So for HCl, we're starting off with 220 grams of HCl. You can just put that over 1 since it's an extensive quantity. And the molecular weight of HCl helps us do a grams to moles conversion. Once again, we're going to have to look at our balanced equation to figure out what is our mole to mole conversion. And using the coefficients from our balanced equation, we see that we have a 16 to 2 ratio. And then last but not least, just like we did before, we're going to do a moles to grams conversion. When we do the math here, we are going to find out that actually, according to the HCl, we are only able to form 95 grams of our manganese chloride. And so based on that fact, we can say that since our 95 grams is a smaller amount than 130 grams, HCl is going to be the thing that runs out first. And that means that HCl is our limiting reagent. And so conceptually, what's happening here is we're sort of going through a journey for each of the ingredients of a recipe and figuring out what's going to happen as the recipe goes along. So as I start to form manganese 2 chloride, let's say I formed 60 grams of it. That's fine. We have enough of each of our ingredients for that to happen. Forming 90 grams, still totally fine. As soon as I form 95 grams of the product compound, I no longer have any leftover HCl. I've used all of it up. And so even though the potassium permanganate was like, hey, I could form up to 130 grams, HCl is bowing out of the equation. And so when we say limiting reagent, we're really just talking about the thing that runs out first. And using this kind of strategy where you calculate the maximum amount of product you could form with each of your ingredients, that can help you determine which of those compounds is going to be the limiting reagent. Okay, so step 3, we need to now figure out how much of our manganese 2 chloride was formed. And we just talked through how this 130 grams is not actually something that can happen in real life, because while potassium permanganate would be happy to form more manganese chloride, because HCl is the limiting reagent, this 95 grams of manganese 2 chloride is the only thing that matters. And so one question that I'll frequently get from students is, when we did this process, why did we have to go all the way to grams of manganese 2 chloride? And why did we choose manganese 2 chloride instead of one of our other products? The answer is that actually both of the things that you just described, either stopping at moles and comparing or computing it with respect to a different product, would be totally fine and will allow you to determine the limiting reagent. However, I always like to determine the product that the problem statement asked me for in the units that the problem statement asked me for, because that always makes step 3 really easy. And so we can go ahead and simply write down that we already did this. And so we've already got our final answer. Okay, so looking back up at our problem statement one more time, we see that we were asked 2 questions. The first was how much of our manganese 2 chloride we were going to form. Now we know that that answer is 95 grams. You'll notice I'm using 2 sig figs here because that's what the problem statement gives me. However, we still need to figure out how many grams of the excess reagent will remain. And so that's going to be our next task. My strategy here is going to be to go and use stoichiometry one more time. This time, we're actually going to calculate, based on the fact that we know the limiting reagent, we can use stoichiometry to determine how much of our excess reagent is going to be used up during the reaction. And so I am going to go ahead and start one more time with my HCl, which we have 220 grams of, and say that our 220 grams of HCl does correspond stoichiometrically, in other words, in a mole to mole ratio, with how much of our potassium permanganate gets used during the course of the reaction. And so we'll need to do one more time a grams to moles conversion. Followed by a moles to moles conversion. And from the coefficients in our balanced equation, we had that there was, should be looking at my balanced equation, 16 moles of HCl for every 2 moles of KMNO4. And I do want to calculate this quantity of potassium permanganate in units of grams, and so we'll use our molecular weight for potassium permanganate one more time to determine that we have 158.03 to figure out how many grams we've used. Plugging this all into my calculator, I am able to figure out that the number of grams of HCl that gets used is equal to 120. However, we're not asked how much of the excess reagent is actually used. We're asked how much of it is left over. And so our strategy to finish off this question is going to be to subtract and obtain the difference between the starting amount of reagent, which was something that was given to us in the problem statement, versus the amount that we used, which we just calculated in the previous step. And so knowing that we can say that the leftovers is the difference between the starting 160 grams that we were given, subtracted from the 120 grams that was just used. And that gives us a difference of 40 grams of potassium permanganate. That is what is left over in this reaction and is the answer to part 2 of this question. Now, as kind of an optional strategy, there is something that you can use as a table organizational tool to help conceptualize the difference between starting amounts of reagents, how much gets used in a reaction, and what is left over in the reaction. And some folks call this a BCA table, for before, change, and after. So you don't have to do this, but if you're a visual learner, this may be something that is helpful for you to know when is it that I subtract and when is it that I use stoichiometry. So in our table, because we know that our potassium permanganate is the limiting reagent, we know that all of it gets used up. So to write this change row, I'm going to say that we use 160 grams of it, and after the reaction is over, there is none of it left over. And that's what it means by definition to be the limiting reagent. Similarly, we calculated in step 3 how much of our manganese 2 chloride was formed. That amount is going to be positive, because we're forming this, 95 grams of manganese 2 chloride, which means that at the end of the reaction, we just kind of add these two numbers together and we get that now there's 95 grams of our leftover product. And then last but not least, folks, I have made a terrible mistake. Does anybody spot my mistake? I started talking about potassium permanganate as if it was the limiting reagent. Silly Dr. Vivi. Our HCl is our limiting reagent. So for our potassium permanganate, we'll get to that in a second. We've got our 95 grams of manganese 2 chloride. And then what I wanted to show us was that our excess reagent, potassium permanganate, that we calculated that we used up only 120 grams of it. And so when we add together 160 and negative 120, that gives us our 40 grams that are left over. And so we were asked in the problem to calculate both this 95 grams and this 40 grams, and that's kind of our final answer to the problem. And so that's pretty much it for this video. I'll note that there's a couple different areas or opportunities for us to check our work and make sure things are on the right track. The first is to make sure that our positives and negatives make sense. So if you are ever in a situation in which you're asked to calculate the amount of excess reagent that's left over at the end of the reaction and you get a negative number, you know that you've made a mistake somewhere, frequently because you've incorrectly determined the limiting reagent. The second thing to watch out for is to make sure that our grams make sense. So we should see, if we calculated the other products in this reaction, you would see that the total mass in grams that we start with should match up with the total mass in grams that we have left over after the reaction is over. Because we didn't calculate the other products, we can't do this particular way of checking our work, but it's a useful strategy if there are fewer things on the product side of the equation. And so with that, we have now successfully calculated both of the things that our problem statement asked us for. We were able to figure out that there is 95 grams of manganese 2 chloride that's formed, and we were able to figure out that we're going to have 40 grams of potassium permanganate left over at the end of the reaction. All right, folks, that's all I've got for us today. I'll see you all in class.